Hello and welcome back. In this video I want to look at the code, how we can find the root of the function. This is important because in many applications we need to find the root of the function, i.e. the point where the function becomes 0 or is equal to another function. So one of the most underrated features of these deep learning frameworks like PyTorch or also TensorFlow is that we can work with the inbuilt methods to compute derivatives very efficiently, and this is what we will see is needed in Newton's method. So before we start, how does Newton's method work? So we want to find the function where this is, the point where this function is 0. So we write this as y equals the function plus the tangent at this point, xn. So we need the derivative here to define this. This is like an approximation of the function. Now we say we want to write the root of the function, so y equal to 0, and then we can rearrange this. It becomes this term. So assuming we have a derivative and it's not equal to 0, we can solve. Because this doesn't give us the root directly, Newton's method gives us an iteration. We can say the point x, or where the root is, or where the function becomes 0, can be iteratively estimated by taking the xn and then taking the previous iteration minus the term of the function value minus its derivative, and so on. And we can keep doing this until we reach a certain precision. Key thing is that we don't have, we need a sort of initial guess that needs to be sort of suitable, needs to be not too far away, where we can always estimate this within reason. So in this example, we take a very simple function, cos of x minus x. So we define this as a PyTorch version. Key part is here that it needs to be a tensor because we need the derivative, as you've seen. And so we just first plot the function. You can see it's sort of a wavy line down. Essentially minus x is the line down, and then we have a little bit of a wave on the cos part to it. Now, if we do this, and we already then know, if we solve this analytically, that the root of the function at the point where it crosses 0 is given at x.755, and this is what we want to estimate now numerically. How do we do this? So we can implement PyTorch methods. So we have the x, right? So this is our x value. The key thing is that we now require a gradient, so we can track it. We give it tolerance and also max number of iterations, so it doesn't run forever if something doesn't converge. And then the key thing is for a number of iterations, we take the value of the function and then compute the gradients. And this is then essentially Newton's method, right? So we have x new, or xn plus 1 is x, the old one, minus y divided by the gradient, the derivative. And then we have, if the convergence criteria, if we are within a given tolerance, then we sort of stop and break out of the loop. The key thing also happens here now for the next loop. We need to make sure that we detach the old x value from the previous computational graph. So we start a new iteration, and we also require the gradient. So this is essentially replacing this line here. We initialize the variable, and here we overwrite it with a new PyTorch tensor. If we take it with the value that we had before. So this will typically work well, especially if the function is well behaved. But we can also make use of the optimizer and all the methods that are within PyTorch. So we can make this a little bit more PyTorch-like. If you like, we still have our value of the function here. We have the convergence criteria, and now if we want to use the optimizer, we need to define a loss function. So here we say, okay, we want to have it at 0. So essentially 0 minus y. This is our mean squared error, and since of course 0 minus y is essentially y. This is our loss function, and we'll add a small epsilon so that this doesn't get 0 or diverge. And then we can take the propagation with the optimizer beforehand. If you want, you can also clip the gradient, so if the gradient gets too large, and then we take the next iteration. And then you can see that in this example it takes a lot longer, and then it depends on the problem at hand if the direct implementation of Newton's method is more efficient, or if using an optimizer is better for your case.